we'll be going through machine design. Okay, so this is the syllabus for your GATE exam. Okay, so it has been classified as applied mechanics and design. Under this, we have totally 5 divisions. Already we have finished engineering mechanics and strength of materials. So we are left out with 3: theory of machines, vibrations, and then design. Okay, so today we'll be dealing with design. Tomorrow we'll be dealing with vibrations. So design syllabus is this. I'll take you to the next slide. Right. So first, in design syllabus, we have static loading, dynamic loading, failure theories, fatigue strength, SN diagram, principles of design of machine elements such as bolts, rivets, welded joints, shafts, gears, rolling, sliding, contact bearings, brakes, and clutches. Right. So this is the GATE syllabus. Get it. Good morning, sir. Right. So we'll first take up static loading. Okay, right. So when do we call a load as a static load? When there is no time variation of the load, we call it as a static load. If there is a time dependent behavior of a load, we call it as a dynamic load. Dynamic load can be either impact in a shortest span of time, a heavy load, or it can be alternating like plus and minus, or sometimes it can be vibratory. So all these 3 loads will be coming under dynamic loads. Okay? Impact, vibratory loads, fatigue loads will be coming under dynamic loading. Right. So example of cyclic stresses, fatigue loading, right, is what I have shown here, right, a graph between stress and time. So we have a minimum value of stress, we have a maximum value of stress, right. The intermediate value is nothing but the mean, sigma mean. Okay, right. Then from the mean to the topmost, either the maximum or the minimum, we call it as the amplitude, stress amplitude. So this is the example of a cyclic stress acting on a rotating shaft. Okay, this is an example of dynamic load. Always when we design a component, we take care that we give a allowance called factor of safety. Okay, right. So we have an idea on what is the strength of the material. Okay, and also we have an idea of how much load will be coming on the material. So failure stress divided by allowable stress. Okay. So failure stress is nothing but the total strength of the material, the total capability of the material. Allowable stress is nothing but what comes on the member by means of our application, right? So when we divide, we always take n as a whole number, like 2, 3, 4, right? It can go up to 10, 15, etc., etc. Then only we are on the safer side. Okay. So this is called as factor of safety. Right. So first we will see how a component will fail under static loading. Okay. So there were totally 5 theories of failure suggested by 5 scientists. The first one is maximum normal stress theory. It is called as Rankine's theory. Right. So we take a component, we apply a biaxial load, either tension or compression. Okay. At the time of application, if suppose the normal stress at a particular point, okay, reaches the yield value of the specimen, failure will happen. This is what has been said in normal stress theory, maximum normal stress theory. So sigma yt by n greater than or equal to sigma t. Then sigma yc by n greater than or equal to sigma c. Right. So here we make an assumption. Sigma yt is equal to sigma yc. Is it correct? Can anybody speak against this? Sigma yt is equal to sigma yc. We make an assumption. It's just an assumption, but it's not possible. Why we say it's not possible? Tensile load is a pulling load. Okay, atoms move away from each other. Get inside. When you say compressive load, atoms are going to collide against each other. When they come in close contact, one will glide over the other, called slip, dislocation, twinning. All sorts of yielding mechanism will happen in compressive loading. So a material will fail easily in compressive load when compared to tensile load. But to find out solution to real-time problems, we need to make certain assumptions. We need to use mathematics. That is why we use this assumption sigma yt is equal to sigma yc. Okay, so this is the assumption sigma yt is equal to sigma yc. So this is a biaxial system. We plot sigma 1, we plot sigma 2, then we plot sigma yt, right? And if we complete the points, okay, it will be in the form of a square. This is called as design space. So our loading should come inside this design space to be on the safer side, to avoid catastrophic failure. Okay, so now this Rankine theory, where it can be applied? It can be applied for tensile loads, it can be applied for compressive loads, but the material should be strictly brittle material, right? We cannot apply it for a ductile material because this is purely based on normal stress theory, maximum normal stress. When you say normal stress, it's very simple, giving a punch on the wall. It's a pressure actually. So we are not dealing any shear here. So we can deal only with brittle materials using this theory. It can be applied for glass, it can be applied for cast iron. Okay, when it comes to ductile material like aluminum, steel, you need to go to another theory, right? Okay, right. So the next one, maximum shear stress theory, right? So here we say that yield strength in tension divided by factor of safety should be greater than difference between principal stresses. Okay, sigma 1, sigma 2, sigma 3 are principal stress. First understand what is meant by principal stress. This is nothing but a stress component where there is only normal stress, there is no shear, that we call it as principal stress. The plane in which this principal stress is acting is called as principal plane. So when you take a component, you apply a load. When we apply a load, the object, any object on earth, will adjust in such a way that, okay, it will create three principal stress, three principal planes. Other than these three principal stress and principal plane, wherever we go, there will be a shear component. What is meant by shear? So simple. Take a paper and tear it off. That's the thing about your shear. You need to understand what is meant by normal, what is meant by shear. You should have a clear understanding. Okay, so take a paper, tear it off. That will be nothing but your shear. Just a minute. Okay. Right. So we take a, we are once again we are taking a biaxial system here. When the loading is happening at any one point, the stress value has reached in such a way that it is equal to difference between the two principal stresses, then yielding will happen, failure of the material will happen. That is what this theory says. Maximum shear stress theory given by Tresca or Guest theory. Okay, right. So it's applicable for shear stress. When you apply a load, that load should be shearing in nature. Then only you can apply this theory. And it is applied for ductile material. You know that ductile material can be pulled very easily. There will be elongation. It's not like brittle. When you say brittle, example glass, you drop it, it will break off. There is no elongation, deflection, expansion, nothing is present. Right? So the next one. Right? So maximum strain theory, Saint-Venant's theory. It has been suggested that you take a biaxial system, right? So at a particular point, the stress value, when it is equal to this much amount of stress, okay, right? One principal stress minus Poisson's effect into another principal stress. When this value is reached, yielding will happen, failure will happen. Okay, right? So when you bring this mu, okay, lateral effect, strain is coming into the picture because it has been strained, that strain theory. This is nothing but strain, okay, sigma by m. So it can be applied only within Hooke's law. Okay, in the Hooke's law range only you can apply this theory. If it goes beyond this Hooke's law, there is a 2 points for steel. One is called the upper yielding point, other one is called the lower yielding point. In between these two regions, this theory cannot be applied. Okay, so only within the proportionality limit you can apply this, because stress is coming into picture and as well as strain is coming into picture. Okay, right. So this is the design space. Your loading should exactly come in this rhombus region. Anything beyond this, say for example this point, okay, away from design space, you will lead to failure. Okay, right. Next one. Right, maximum strain energy theory. Okay, right. This energy theory states that instead of dealing with stresses or instead of dealing with strains, please deal it with strain energy. What do you mean by strain energy? Half into load into deflection, or half into stress into strain. Okay, this will give you somewhat more and more accurate results for failure, capturing the failure phenomena. Right, so you take a biaxial system, right? Under the biaxial system, when the strain energy at a particular point reaches this value, you say that failure is going to happen. Okay, right. So this is an the design space is elliptical in nature. You are plotting sigma 1 on x-axis and sigma 2 on another axis, y-axis. So right, so this is the major axis, this is the minor axis. So these are all the length of the major axis and length of the minor axis. So therefore, when you are using stress and as well as strain, because Poisson's effect has come into picture, strain will also come into picture. Since you are using stress and as well as strains, this is also applied only under the Hooke's region. Beyond this, this theory cannot be applied. Okay, right. Right. This is was given by Beltrami-Hicks theory. Okay. Right. The next theory is von Mises theory. Right. This is called as the von Mises theory, the most accurate theory to judge a failure mechanism. Okay. It really says that we have to calculate the total strain energy per unit volume divided into two. One is called the dilational part, other one is called the distortional part. This distortional is due to shear. This dilation is due to pressure or normal stress. Okay, right? So in this, when this distortion part, okay, reaches a particular value, right? This particular value, this is called as U distortional. Failure will happen in a biaxial system at a particular point when the strain energy, right, distortional energy reaches this particular value. Failure will happen. Okay, right. So there are several cases. If there is only principal planes, what will be the criteria for failure? This will be the criteria for failure. When only there is a plane stress condition, this will be the criteria for failure. And when there is only pure shear, this will be the criteria for failure. So if your yield value reaches root 3 times sigma 1 2, you land up in catastrophic failure. Okay, right? So among all, this is the most accurate theory for judging a failure mechanism. Right? See, wherever you go in this static theories of failure, you will find one phenomena. Either square term is coming or a multiplication term is coming. Right? Get it? Right? For example, you take this here. Square term, right? Product term. Okay? So what will happen? Can anybody judge? When you square a value, what will happen? Minus 3 square is 9. Plus 3 square is also 9. Then what is the use of significance of minus and plus? Do you really understand what I'm trying to say? Why we go for dynamic fatigue loading? See, this theory cannot judge whether it is a static, compressive load or a tensile load. It will not catch hold of the directional property. When you square a value or multiply by two values, the directional property is lost. the direction of the loading is lost. Okay, right? So it will not handle fatigue stress. It will not handle vibrational stress. It will handle only static stresses. That's the reason we go for the next one called the dynamic loading, fatigue loading, right? So this is the reason why we are going for another theory, right? So these are the conclusion. So all the five theories have been plotted in sigma 1 versus sigma 2. So this is the design space, okay, right? Each and every theory. And what is the region? Normal stress square, shear stress hexagonal, strain rhomboid, strain energy ellipse, distortional energy circle. Okay, right? So this will not catch hold of the varying stresses. It will not catch hold of plus and minus effect. Only one effect, squared or multiple product of the terms. Right? Okay. So before that, we will right. So this is the stress strain curve for mild steel. Okay, right? So up to point P, this is point P, right? Stress is proportional to strain. This is called as proportional limit. Okay. Beyond this, this will be linear, but it will be non-linear in nature. Here also your Hooke's law will get satisfied, but it will be non-linear in nature. P to Q. Then from Q to R is called as the upper yield point. S is called as the lower yield point, right? So there are P is the proportionality limit, Q is the elastic limit, R is the upper yield point, S is the lower yield point. This is the stress strain curve for the mild steel material. Okay, right? Okay. Right. Then how will a brittle material look like? Brittle material will not show yielding. For example, glass, you drop it down, it will get converted into pieces. Right. So this is how the loading will look like, stress versus strain for brittle material. For other materials, this is for mild steel, this is for rubber, this is for elastic plastic material, low ductile material. These are the various stress strain diagrams for different sorts of materials. Right. So you need to understand each and every material cannot be free from void or cracks. Okay? Any raw material will always have void and cracks. So at that time, if you give some variation loading, okay, it will fail so miserably. In this crack region or void region, the stress calculated will not be as per your formula. Okay, crack or void diameter is so small, and this diameter is sitting in the denominator. Anything divided by 0, what will happen? Undefined value. So stresses will reach very high values. So all of a sudden will lead to failure. See, a steel, take a steel ball, you throw it on the wall, okay, wall will break off. Same steel, convert into a thin wire, okay, bend it, straighten it, bend it, straighten it. Do it just 5 to 10 cycles, that wire will break off. This is called fatigue loading, okay. So there is no need that you should reach yield point. Before yield point itself, the stress is very low, but if it is directional in nature, plus and minus, it will break off. Up to certain time, we were all worried for only infinite life. For example, if I design this fan and if I start operating, my aim is that it should come for several years. I will not specify number of years like 2 or 3. What happened in terms of wartime? It was in 1940, 1940 or 43. They built one huge bridge. Okay, bridge will have its own natural frequency, and when wind is blowing across the bridge, that will also have its own natural frequency. When both the frequencies are coinciding, the bridge will land up in resonance. It landed up in a torsional mode of vibration, and the huge bridge, okay, collapsed down. Then only they suspected that there is one more loading other than static loading. Yeah. So people were going for only infinite life in the previous design before 1940s. After this phenomena happened, after this phenomena happened, they started to concentrate on vibrational loads and as well as fatigue loads. Okay, right. So what is meant by endurance limit? The stress amplitude, okay, of a material when it completes 10 power 6 mil number of cycles before failure is called as endurance limit of the material, right? Then what is meant by stress concentration factor? ratio of endurance limit of a notch free specimen divided by endurance limit of a notched specimen. See, to catch hold of the void and cracks only, we are putting a notch in the material and then we are going to break it. Okay, bend it, straighten it, bend it, straighten it. Crack will travel and you'll end up in a total catastrophic failure. Right? Then what is with this notch sensitivity? How can it be defined? It can be defined using this formula. It can be designed using this formula. Okay, right? So what is meant by Kf? Stress concentration factor, actual stress concentration factor. Kt is nothing but theoretical stress concentration factor. We bring in actual and theoretical simply because mathematics is different, experiment is different. Okay, that's the reason why we bring in Q. And even though you are an engineer, okay, it is not necessary that, or it will not be sufficient that for all real-time problems you can get a solution by only experimentation. You cannot do so. Okay, at certain places you need to believe in imagination, mathematics, approximation. Then we can get the answer. So this fatigue sort of loading, okay, each and every time you cannot do an experiment and find out the life. So that's the reason why we are bringing in all these variables, Q, KT, KF, right? Okay, right. So when you bring in variables, obviously we'll have two categories. One is actual, other one is the theoretical. Right. So this is how it looks like. Okay, so Howler curve or SN curve for mild steel. Okay, it's a plot between sigma in y-axis. Okay, amplitude of stress cycle in y-axis to natural logarithm based on of cycles, number of cycles. Okay, so this region is called low fatigue. This region is called high fatigue. When you go beyond this, it is called infinite life. Okay, nowadays we always bother for the finite life because we know that we cannot escape from vibrational and fatigue load. We give a component to the customer, say that it will come 2 to 3 years. After 2 years, come back once again. I'll give a newer one. Please fit it. So we are all worried for only finite life nowadays because we cannot escape from fatigue loading and vibrational loading. These two loading will not, somehow or the other come inside. Right. Okay, portion up to 10 power 3 cycles is called LCF. Okay, right? And more than 10 power 3 is called as HCF. After that, the curve becomes asymptote. Asymptote means this curve will touch x-axis at a very far distance, undefined or infinite. Okay, this is the endurance curve for mild steel. Right? We do have damage criteria. Okay, we assume that in a component, first bending load is coming, then torsional load is coming, then axial load is coming. Right? Several loads, several types of loads, and each and every load is having a cyclic part. Okay, under that, what can we do? Add each and every load Ni by Li. Okay, what is N? Stresses of variable loadings, average and variable stress, like bending, torsion, axial. Okay, N is nothing but the small n is nothing but the type of loading, bending, torsion, axial. Capital N is nothing but number of cycles at actual loading. Then Li is nothing but number of cycles at failure loading. Failure will be at some other point. Okay, actual load will be nothing but our day of operation. So divide both. Say for example, you are doing for bending. Add it with torsion, then add it with axial, and equate it to C. This C value has been found between 0.7 to 1, and find out what is the cycle for the given loading. How much will it withstand? Okay, to find out the life, we are using this minus rule cumulative damage criteria, right? And fatigue failure criterion. Okay, 3 people: Gerber, Soderberg, Goodman. See, actually, Goodman plotted between endurance limit and ultimate tensile strength for brittle material. Soderberg gave the criteria for endurance limit and yield, that is meant for the ductile material. Okay, Gerber parabola also gave a correlation between endurance and ultimate tensile strength of the material. So whatever experiment we do, okay, all the plotted values should come in this region. If it is beyond, above or below, this shows that we are going to land up in failure so easily. This is the design space. Among all the three, this Soderbergh is a very conservative criteria, safe criteria. Goodman line occupies between Gerber and Soderbergh. Okay, right. And when do we take up Gerber's parabola? If the material is having non-linear behavior, loading is showing non-linear behavior, at the time we go for Gerber's. Okay, right. So sigma E means endurance limit, UT means for brittle material, YT yield strength for ductile material. Sigma V is nothing but stress amplitude. Sigma A is nothing but the mean stress. Okay, right. I have given this. So when do we apply? There is one more criteria, modified criteria for Goodman's. Okay, this is meant for fluctuating axial load, bending stress, and fluctuating torsional stress. Okay, so modified Goodman's criteria is a plot between sigma y in y-axis and sigma y in x-axis. We will see when to adopt this. Okay, and when we do the problems, we'll know. As of now, we can take down as modified Goodman's criteria for higher factor of safety. You can adopt Goodman criteria itself. When you need higher factor of safety, we can go for this modified Goodman's line. Okay, to be more on the conservative side. Right, just a minute. Right. So these are all the equation governing the endurance strength, fatigue strength. Okay. So sigma E is nothing but our fatigue strength. That is our criteria for dynamic loading. N is the factor of safety. Sigma Y means yield stress. UT means ultimate tensile stress. Right. So first we will take riveted joints. So any doubt as of now? See, because we have got 7 hours today. Hardly I can go through for 2 hours for brushing your fundamentals, and the remaining 1 hour will go for lunch. 3 hours goes away. 4 hours will do problems. So any doubt, please stop me and ask then and there. So you're comfortable now for static loading and dynamic loading, right? So we will go for design of machine elements. Okay, riveted joints. So the first one, what are all the terminologies in riveted joints? Main terminology is pitch. Okay, center of one rivet to center of another rivet. This is called the pitch. Okay, this is the main criteria. So pitch length means P. Sigma T and sigma C means permissible tensile and compressive stresses for plate. Okay, tau is nothing but shear strength of the rivet material. D is nothing but diameter of hole in the plate. T means thickness of the plate. N number of rivets. F force applied. So what are all the failure that you can come across? Can anybody of you say? What can be the failure that can come across? Yeah, shear is a conventional failure. There are further failures also. See here, we will be designing the plate and as well as the rivet, both. So when you say tearing of plate, so this is the plate and this is plate, okay, right? I apply force and I'm going to pull it off. So what will happen? I assume this is the rivet. This rivet will get converted into 2 pieces. So this is single shear. I assume there are 3 plates, okay, right? Shear will happen at 2 areas, one above, the one below. This is an example of double shear, right? So rivet remains safe, but what has happened? The plate has got torn off. That is called crushing of plate or tearing of plate. So the first failure is tearing of plate. Okay. So what we do is that I want this area. Okay. So what we can do is in this pitch, you can subtract this radius and this radius, nothing but 2 into radius will be diameter. So P minus D into thickness of the plate into the ultimate tensile strength. Okay, this is because tensile loading. That is why we use sigma T. Right. Then shearing of rivets, single shear, double shear. Okay. So the shear force is nothing but area into shear stress. Shear stress is nothing but tau, pi by 4 d square. right? If it is double shear, you need to multiply by 2 because there are 2 shears. Then crushing of rivet. See what will happen. This is the rivet. Totally, it does not land up in a failure. Instead, it looks like this. When you apply a load, right? So, what will be this area? Right? What will be this area? Thickness of the plate into the diameter of the rivet. So D into T into N. N is nothing but number of rivets into, since this is compressive in nature, we use sigma C. Okay, sigma YC. We need to take the value of yield in compression. When it is tearing of plate, we need to take sigma T. Okay, ultimate tensile strength of the plate material. Okay, right. So you have any idea? So any component given to you, first you need to have an idea of loading. What are the loads that you are going to come across? This is number one. Then you need to have an idea of what are all the failures that you can come across, what type of stresses are getting induced. Then you need to have an idea of which theory to apply. Then get the whatever variable you want, thickness, diameter, life, factor of safety, whatever you want, you get it. Right. So I hope you're clear with when to adopt static failure theories and when to adopt fatigue theories. Right? When will you adopt fatigue theory? Anyone come out? When the load is cyclic. Okay, sigma applied is itself plus and minus. Tensile stress, compressive stress. Tensile stress, compressive stress. Okay, at that time you need to use fatigue loading. Shortest span of time, heavy load. For example, an accident. This is nothing but an example of impact load. Whereas I'm just taking a hook, or say for example, yeah, this fan is not running now. I'm attaching this fan and I'm going off. An entire day it's going to hang. This is going to come under static loading. So please understand when to use what theories. Right? And all the theories of failure, if you take that terminology, okay, the expression or the equation, either square term or product will be present. Okay, so if I use sigma 1 is equal to minus 3 and sigma 2 is equal to minus 3, when you multiply, the minus sign will get removed off. When you square also, minus term will get removed off. So static theory will never capture the dynamic variation. Right. Okay. And when you use the cross sectional area, please be careful. Okay, don't interchange. This is actually rivet. I'm going to pull it like this. So diameter into the thickness of the plate will give you the cross sectional area of failure. Similarly here, I'm just going to divide into two parts, and if I see this, it will be circular. So pi by 4 d square. You understand? Then if you take the first one, this is the area of failure. Okay, tearing of plate. So how will you get this? P, remove this distance because there is an empty space here of the rivet. So here one R, here another R. So P minus D into the thickness of the plate. That will be nothing but your tearing area of cross section. So first and the foremost, have an idea of what kind of load you are going to get. Static or dynamic, tensile or compressive, bending or torsion. That idea you need to have, number one. Number two, okay, what kind of stresses that you are going to come across? Tearing, crushing, shear, the normal tensile, normal compressive. That you need to have an idea. Then number three, please write down properly the area of cross section of failure. That is number three. Then use proper theory to find out whatever you want. Okay, this is how your questions will be. Okay, this is riveted joints. Next, we will go to the welded joints. First, I'll come across the terminologies. Okay, T means throat of the weld, right? This distance, this is the weld, this is the welded portion, right? So this distance is nothing but T, or this distance is nothing but T. We decide this throat based on the thickness of the plate. Okay, right? So throat is the minimum height of the weld, this height or this height, minimum height of the weld. Why we take a minimum value? Then only the stress induced will be very high, and accordingly we'll put the material. Accordingly we will select the factor of safety. That's why we are taking the minimum. Right? Okay. So consider a simple fillet weld. This is a fillet weld joining two plates of thickness T. This is also called as leg. Either we call it as throat or we call it as leg. Length L subjected to tensile force. So this is T, this is T. Find out this distance. This will be T by root 2. This is nothing but throat. Okay. So first type of stress that I'm going to come across will be tensile stress. Okay. If the weld is subjected to a tensile force across the weld length, the average tensile stress in the weld is given by F by TL. T is the thickness, L is the length of the plate. Okay. Right. So this L into this T. Right. One dimension is L, perpendicular to the board. Other dimension is T by root 2. So if I draw a rectangle like this, that will be the minimum cross-sectional area, which will give you a maximum value of stress. Accordingly, we need to set a material and factor of safety. Right? So sigma is equal to F by TL. Then you will be coming across shear stress at the same area. Okay, right? So if you see this, crushing action is going to happen like this. There is one force F here, another force F here. So when you pull it like this, shear will be in this region. Okay. So therefore, T by root 2 is nothing but the breadth, and this is the length of the weld. So tau is equal to F by TL. Okay, got it? So these are all the two failure stresses that you're going to come across, with which the material can, with which the weld will fail. Okay. Now, for single fillet weld, okay, it will be T by root 2 into L. We are not going to put T here. We are going to put T by root 2. This will only give me the minimum cross section. So this root 2 goes to the numerator. So root 2 F divided by TL. And if suppose there is a double fillet weld, this is a double fillet weld on both the sides, top side and bottom side. So you need to multiply by 2 in this expression. Okay. So 2 TL you have to put. So F divided by root 2 TL. Got it? If you don't understand, please come out. Don't be hesitant to see. If you keep your doubts inside, it's called incompletion. Okay, it will start growing and will start getting applied to all the information that you have in your mind. So please clear off your doubts then and there. Don't allow it to grow, or don't allow it to accumulate. Your confidence level will be very low. Okay, same welded joint. Okay, so this is an example of eccentrically loaded weld, right? Assume it's a cantilever beam. You're applying some load here. Okay, then this is the cross section that I've shown here. So at that time, how will this? What are all the stresses that can you come across? See, I'm having a weld here. Okay, I'm going to apply a load like this, so it is going to break like this. This is called primary shear. That I've shown it here. Same expression, F divided by T by root 2 L. Instead of T, we are putting T by root 2, because that is the very critical region. Okay, throat region. Right. What is the another stress that can come across? Can anybody say? Yeah, bending. So when you bend like this, F into E will be opposed by the shear force in these two rivets. Okay, sorry, these two belts. So this is clockwise, they will give you anti-clockwise. That will be an example of secondary shear. So secondary shear is arising primarily due to bending. When you use the word bending, there is a bending stress and as well as shear due to bending. If beam is so short like this, and if I apply a belting load, shear can be neglected. If the beam is very long and if I apply a bending load, obviously there will be a tearing effect. That is called as shear stress due to bending. Okay, that was being considered here. Secondary shear stress. M by I is equal to E by R is equal to sigma by Y. That is what I have written it here. Right. What is meant by J here? Anybody? Polar moment of inertia. Because this shearing effect will be resisted by inertia along x-axis and as well as y-axis. That's the reason why we are taking it as polar here. So if this is the rivet weld they are looking at, you have to take it at the axis perpendicular to this. So both y and as well as x. Okay, right. What do you mean by area? Simply, what is meant by inertia? A mass is moving. Resistance offered by a mass for change of state. This is the general definition for inertia in dynamics. What do you mean by area moment of inertia? Resistance offered by an area against deflection. Okay, wow. That is in simple area moment of inertia. When there is a torsional loading, resistance offered by an area against the deformation. This is how you need to answer in interviews. Okay, if they ask you what is the physical meaning of area moment of inertia, polar moment of inertia, you have to say like this: resistance offered by an area against deflection. Area moment of inertia, AMI. Resistance offered by an area against deformation, nothing but polar moment of inertia, PMI. Right, then what is meant by product moment of inertia? See, there are certain structures called plates. So you take a plate, apply a mid load, center load. What will happen? It will deflect along x-axis and as well as it will deflect along y-axis. Deflection of x-axis will be aided by deflection along y-axis. It will be from the form of product. So when you apply a load, resistance will come as a product of both the axes, both the degrees of freedom. So that we call it as product moment of inertia. It is applied for plates. Okay, right. So all moment of inertia I have explained. Right. So here we need to use J because resistance against shear will happen in both x and y. Right. So T is the throat, minimum height of the weld. That is a critical cross section where you can come across maximum stress. Accordingly, you can select material and factor of safety. Then bending moment on welds. Okay. Here eccentric load. Here we are applying the bending load. So here first one is as usual primary shear, nothing but the cutting action. The second one is due to the bending. Okay, M Y by I, simple bend. Okay, we are going. This is the rivet. So this is the fillet weld. We are going to bend the weld. Okay, so M Y by I. It is not J here. This is simply pure bending. Okay, so what will be the maximum shear stress due to bending plus due to torsion? Square root of sigma by to the whole square plus tau 1 square. Got it? Are you able to understand? This loading is different from this loading. This is eccentric load. This is nothing but bending load. Right. Any doubt? If doubt is there, please ask me. Yeah. Bending stress that arises due to a bending load. See, this is my cantilever beam. I apply a load like this. It is going to bend downwards. When I bend downwards, top fibers will be under tensile, bottom fibers will be under compression. The tensile compression value is nothing but your sigma b. Got it? Where? No, this is we are taking it from Mohr circle. See, here primary failure stress is nothing but shear. If you take Mohr circle, it will be like this. This will be sigma 1, this will be sigma 2, then this value tau will be equal to sigma 1 minus sigma 2 by 2. This is for bending. Then due to bending, then due to torsion will be simply sigma 1. So this value you are squaring it and this value you are squaring it. Here bending, there is only 1 and 2. Two loads can come for bend. Only one load is given. So when sigma 2 turns out to 0, you will be left out to sigma 1 by 2. That is simply put it as square. Got it? Why we are doing? Do you understand? These final expressions are always coming from Mohr circle. Okay, where we plot sigma 1, sigma 2 along y-axis, x-axis, get the values of shear. Right. So do you understand the difference between these two? Okay. So here we are having a plate. This is the welded joint. Load is acting away from the welded joint. This is nothing but your eccentric loading. Whereas this load is concerned, your rivet is like this, perpendicular to the board. But load comes as a bending load. We are going to bend the rivet. Right. And in this loading, resultant stress at any point will be vector sum of the forces caused by the two stress. Just add sigma 1 and sigma 2 and get the resultant value. But here you need to come out as a square root. Okay? Because bending happens in one direction, torsion happens in another direction. But these two are acting in the same plane. That's the reason why directly you can add it. Two forces are along x-axis. Two forces. Simply you can add it. When one is along x and one is along y, what will you do? Root over fx square plus the fy square. That is the difference between these two. Okay. Okay, boys, this is threaded joints, screws, nuts will be coming under this threaded joints. So ISO thread designation, International Standard Organization, says that it's M20 cross 2. What does it mean? 20 means nominal diameter, 2 means pitch, right? So here I have a plate. Okay, I have a plate. I have one more plate like this. This is plate 1. This is plate 2. I'm using 4 joints here. 4 threaded joints. 4 screws you say. 4 bolts, right? So I'm applying a eccentric load here. This is eccentric load. When do you say it is eccentric loading? Can anybody say? See, you have certain joints. Joints will have a center of gravity. If load is passing through center of gravity, it's normal load. Load is deviated away from center of gravity, you say it as external loading. Okay, wow. Right. So what can be the load, what can be the stresses that can you come across? Can anybody say? Yeah, bending stress will be present. Yeah, shear. Right. So first and the foremost, okay, see, I assume I'm taking a thread 1 like this, okay, right? So I'm applying a load here. So it's going to get cut like this. This is a direct shear. We call it as primary shear. Simply force divided by area. If you see, when I break like this and then I will look at this, it will be a circular cross section. That is why I am putting it as pi d square by 4. Okay. What is only secondary shear? See what happens. This load will create a moment about the common center of gravity of all the 4 threads. To resist this turning moment, okay, these these threaded joints will give rise to one more shear, right? So what is going to be this one? Clockwise. F gives clockwise moment. Okay. So what will happen? This is clockwise. For creating anti-clockwise, this thread will give F2. Okay. Then this thread will give F2. All anti-clockwise. This will give F2. So moment created by this external load will be cancelled by all the force shear stress, which will give an anti-clockwise moment and bring it to balance, equilibrium. Purida, do you understand what I'm saying? Right. This is nothing but your secondary shear stress. It arises purely due to bending moment. And this shear happens in an axis perpendicular to the board. So resistance along X will be present, along Y will be present. So you need to use J and not I. In your GATE exam, you will be in a very panic situation about time management. At the time, you will mismatch both. Be very careful. Where to use J, where to use I. Sariya. Okay, see, you see this arrow mark? See, I have taken reactions. Okay. This is given as actions. It's creating clockwise, so this will also create clockwise. Simply I have considered reaction here for equilibrium, nothing different. Don't get confused. This is how threaded joints will be designed. Do you understand? What you do, see, learning methodology for GATE exam. You first, we will take machine design as a subject you are going to learn. Yes, right. You see this? See, all the possible formulas of entire design has come. First, what you do, you go through this and write once fully by closing the book. Okay. Then you go for solving the problems. When you solve each and every problem, what all the concepts that I said will get captured automatically. Where you have to use I, where you have to use J, whether the loading is eccentric or whether the load is bending, everything will capture. Okay. You have to solve all the problems. Take 20 years of question paper. This is 2024. February month is over. So what you can do is you can start from 2004. From 2004 to 2024, solve all the problems. I'll show you how I'm going to. This is how I prepare. See, GATE 2006. First, what you do once, first attempt, take the calculator and completely solve it and understand first. Next attempt, try to solve by yourself by closing the book. At that time, you need to certain times you need to open it. Certain will be under your memory. When you do it for the third time, fourth time, obviously you will get all the logics captured, all the concept understood. So 20 years of GATE question paper to be practiced by yourself, minimum of 2 to 3 times will fetch you 99.999, and any one of the IITs will get MTech. That is compulsory. Okay. Of course, there are people who are born with very strong IQ who don't need all this. I'm speaking at an average level, both bright and as well as a dull candidate appearing for GATE. and learning methodology is concerned, you can combine any 2 persons per team, not more than 2, because you should not land up in loose talks, diversion, distraction, this, that will come in. So you can club by 2 members per team. Don't go for isolated learning. Solo learning will not help. People born with strong IQ, it will help. People born with average IQ, if you go and sit lonely, you will have diversion, distraction, resistance from mind. Your mind will not get fixed. So what you can do, 2 of them can combine. Same place, better far away place, through cell phone. So discuss one by one. When you discuss, obviously when you come here, why t by root 2 is taken, you will understand. I'll take it. Yeah, this will be the region of the where there is a very minimum cross section. Only in the minimum cross section, stress will be maximum. Accordingly, we can select the material. So this sort of concept will come automatically. If you don't have knowledge, if you don't have IQ, don't do anything, don't panic. Just to discuss with others, you'll get the logic. It will happen. So this is how you need to prepare. Okay, okay, here we were. Design of shafts. You know what is a shaft? It's a machine element that is meant for transmitting power. Power means torque will be present, speed will be present, both. Torque and speed will be power. From one shaft to the other, input to the output. So whenever you use the word shaft, shaft is primarily a function of piston because it's rotating like this, right? So it will be subjected to shear stress. So while shear is concerned, always how to calculate shear in a specimen subjected to uniaxial loading. Okay, always the uniaxial stress value divided by 2 will be nothing here, your sigma y. This is a major concept with which you have to start a shaft, designing a shaft. So sigma y means yield strength of the shaft material. Tau y means shear strength of the sorry, this is not rivet. This is shaft. M means bending moment. T means torsional moment. K is equal to di by d naught. N means factor of safety. Me means equivalent bending moment. Te means equivalent torsional moment. Internal diameter di, external diameter d naught. What do you mean by equivalent bending moment? See, this equivalent bending moment is a bending moment which will create same bending stress when acting alone, okay, equal to acted by a bending moment M and torsional. Okay, so I'll write it here. Bending stress created by Me acting alone. See, Me is alone acting. It will create one bending stress. This should be equal to bending stress created by M and T. This is nothing but Me. Do you get my logic? Suppose it is acted upon by a bending moment and torque. It will create one bending stress, right? That stress should be equal to the bending stress acted by moment alone. That's nothing but equivalent moment, bending moment. Similarly, what is meant by Te? Tau, okay, created by Te acting alone is equal to tau created by M and T. Here I'll ask you one question. Tau comes due to torsional load. Why M is coming here? Can anybody answer? I said before, Can anybody answer? Sorry, pen. Can anybody? Torque will create shear. Okay. Why you are bringing M here? Whenever you say bending, if it is a short shaft, there will be no shear. If it is length, the start is starting from that end and ending it here, a very long shaft. Simply due to the self weight, there will be some shearing action. So shear is also created by bending. Okay, be aware of that. That is why we are combining it as M and T. So whenever you learn gate question, please try to generate some imagination. Okay, conceptualize, understand the meaning of it, and then you learn. So it will be helpful for you to crack the gate exam. Right. So shaft is subjected to simple bending. For hollow shaft, this is the formula. For solid shaft, this is the formula. Shaft is subjected to simple torsion. Hollow shaft, solid shaft, this is the formula. Where K is the ratio of di by d naught. For combined bending and torsion, ME should be taken nothing but half M plus root over M square plus T square. This comes from Mohr circle. Then T is equal to root over M square plus T square. Right? So designed for dynamic loads. Soderberg gave an expression for designing shaft subjected to fluctuating fluctuating bending and torsion loads. So this is the formula. So MA is something but the amplitude of reversing bending moment. TA is the amplitude of reversing torsional moment. KB is nothing but stress concentration factor for bending. KT is the stress concentration factor for torsional loading. MV is nothing but the varying amplitude of bending load. TV is nothing but varying amplitude of torsional load. V means amplitude. It's varying, right? The amplitude is varying. Sigma Y means yield, strength of the material. Sigma is nothing but the fatigue strength, endurance limit. N is the factor of safety. Using this, we can design the diameter of the shaft. Stress concentration factor for bending loads. You can, yeah, they are giving any material here. They are giving material here. Okay, right. I follow Ajay Kumar Samparkar, professor from IIT Kharagpur. That's the book I'm following. Villay Publications. Ajay Kumar Samparkar. I'll give you the ebook. But the problem is that it is under 2015 edition. The recent most have come. 2022 or 23 edition has come. It's an older edition. That I will give it to you. Newer edition PDF is not available. I've searched it. Within few days it will be available. Write it down. Any doubts? If there's any doubt, please do ask now itself. We always select a ductile material for shaft. for maximum transmission of loads. We don't go for any brittle material because shaft will break all of a sudden. Yeah, equivalent bending moment. See, assume that bending moment alone is present. That will create one bending stress. Okay, same value should appear in the applied bending moment and torque. That is nothing but equivalent bending moment. See, we are giving bending moment and torsional load both. Both of these two will create one bending stress. That same stress should be created by only one bending moment. Torque should not be present. That is nothing but equivalent bending moment. What? Equivalent, equal ஆவரணும். So here I'll write equivalent bending moment. This will be similarly moment is creating a stress, shear stress, torque is creating a shear stress. So the same amount of shear should be created by pure torsion alone. That will be equivalent torsional moment. Okay. Okay. So we'll make a move. Okay. Define of keys. You have a flange, you insert a shaft. Hmm? For giving a power connection between shaft and the flange, we insert keys. Keys are several types: square key, feather key, jib head key, saddle key, woodruff key, tangent keys. Okay, based on the type of load transmitted, hmm, safety of factor of safety, we select accordingly. At certain places, bending will be more dominant. At that time, we need to go for the lengthier one. At that time, torque will be dominant. At that time, we need to go for woodruff. So accordingly, we select keys based on the application, right? So if I take a cut cross section of flange shaft key, this is how it will look like. Okay, so the force transmission is like this: one to the left, other one to the right when the shaft rotates. Okay? So what can be the primary stresses that you can come across keys? Right, always shear. Okay, previous. Okay, so when you look from the top, okay, how will be the cross section look like? Yeah, this is how it will look like. That's the reason why we put this as D into L. Are able to visualize how I am calculating area of cross section for failure? Hmm? You need to imagine this, visualize, and then learn. Simply don't learn the formula. In the examination hall, you will mix keys, rivets, and you will write some other thing. You didn't understand. When two of you discuss, obviously a question will come why BL is coming. At the time, it will be clear. Hmm? Right. So similarly, crushing stress. Okay, key can get crushed like this. After a certain space of time, it will look like this due to F here and due to F here. So if you look at this cross section, it will be like this. Hmm? What will this be? Somebody say. You are looking like this. you're looking like this. This portion you're seeing, I'm drawing it here. This will be L. Other one will be T by 2. That's the reason why I'm using L into T by 2. Because it's getting crushed here. Do you really understand? When you apply a load like this half of the thickness will get crushed. That is the area that I have turned here. So you're able to imagine the failure area of cross section. For now, you go home or here itself you can do. Start from the first where rivet, then weld. Imagine each and every area of cross section and first give justification for each and every failure stress. This is how you need to learn. Simple memorization will not help. If you memorize, there is no conceptualization. Okay. See, can anybody tell, since this getting crushed, what type of stress it is? Anybody say? Even you can look at this and you can say, compressive stress. Correct. You have to put sigma c, not tau. For the upper one, you need to put it as tau. Only tearing effect means you have to use tau. Crushing effect means tearing. Paper eduthu kilichingina shear. Very simple. Take a paper and tear, it is shear. Take a chalk piece and break it, shear. Assume one pillar is there. Put a belt and keep tightening and tightening and tightening as possible. There will be nothing but compression, nothing but your crushing stress. If you want, you can write it down. This will be given to you. This material in your hands. Anything you can do. Okay, I'll drink some water and come. So till now, are you clear? See, if you want to learn using this material also, you can learn. What I have done while preparation is that I have taken the important part alone. Say, for example, notations, the diagram, then the type of loading, type of stress, formula. Simply you can learn this also. Yeah. Okay. So design of gears. Okay. See, these gears are called as positive drive. Hmm? While belt chain are concerned, if speed increases, relative velocity between sprocket and the chain, what will happen? There will be some dismantling, and it will get slipped off. Pulley and belt. Okay. So when it reaches a critical value of velocity, the relative velocity will be lost, and the belt will totally come out of the pulley. So we call this as slip drives. Slip coming out. Whereas as gears are concerned, their engagement between two teeths. So we call it as a positive drive. There will not be any slip in gear drives. So we call it as positive drives. But the problem is that the shaft and the driver shaft and driven shaft should be as close as possible. If there is one driver shaft in the wall of this room, another driven shaft in the wall of this room, we cannot put some 10 gears in between. That is not the good way of transmitting power. So they should be very close to each other. Okay, right? And power transmission is concerned, they are limited. Hmm? Right? And so gears are concerned, we can what you can do for enhancing the power, you can reduce on the speed and uh, elevate the torque value. Hmm? Right? So okay. So standard system of gear teeth. Okay. So we know that how to generate a gear teeth profile, either by cycloidal curve or by means of involute curve. Okay. So cycloidal teeth is concerned, it will be very broad at the base, very narrow at the topmost portion. So what will happen is that interference will not be there, and pressure angle will be varying at the engagement and at the disengagement. But manufacturing a cycloidal teeth is very complex. Okay, because of the varying curve. Whereas when involute curve is concerned, it's a bit of a flat curve. So manufacturing is easy, but you will have interference in involute teeth. Okay, yeah. So what we do is that there are two systems. One is 14.5 degree, other one is 20 degree. What do you mean by full depth teeth? Okay, see, 2.25 times of module is nothing but your tooth depth. Okay, to avoid to minimize the interference. Hmm? That's nothing but your full depth teeth. Why do we say it as pressure angle 14.5 and 20? Why not 35-40? See, when you say gear, at the maximum, any gear it may be, the maximum size will be up to my hand. That's all. See, one gear as big as this room. Okay, one gear so small in the watch. This is not possible. Whenever you say gear, it will be always a standard shape, something to my hand level. That's all. This is the maximum. You cannot go beyond. So what you do, you take two circles and then engage it and see. You will find that only at two places called 14.5 degree and 20 degree, grip will be comfortable, power transmission will be maximum, less wear and tear, low vibration, everything will be comfortable, right? So you just merge two teeth and see. Okay, then find out the pressure angle. Only at these two places you are more comfortable. If you keep anywhere between, say, below 14.5, between 14.5 and 20, above 20, okay, you will not have a proper transmission of power. That's why it has been said that these two are the standard values. Okay, You take any arbitrary two circles, you engage it and see, you will always land up in a place where 14 or 20 is coming. Other places you will not get it. You will not be comfortable. Okay, right? That is why it has been put as 14 and 20. Right. Certain times what we can do, full depth will be very lengthy. So when two teeth come in engagement like this may totally knock off, called interference. To avoid that, you can use, we can cut down the some full depth and call it as stub. Interference can be avoided. Right. Other one needs to use a cycloidal, but very difficult to manufacture. One more thing you can do is that without affecting the velocity ratio, to certain extent only we can vary the center distance. You cannot be keep on varying center distance for years. It's not possible. I said always both of them should be close to each other. So without altering the velocity ratio, you can slowly move the center distance, and somehow or the other, by using invalid teeth itself, you can reduce down the interference. These are all the gear failure mechanisms. Okay, right. So our concern is always interference when gear is concerned. So to avoid interference, what is the number of teeth on pinion? Pinion is always a smaller fellow called a driver. Always we give small size for driver and we give a larger size for driven. Why? Why we do so? Any object starting from rest will give resistance to us for moving, called inertia. To overcome the inertia, to gain sufficient torque, we always put pinion as a smaller one and driver as a bigger one. Then only for several revolutions you can pull the vehicle. Your two-wheeler, first gear, second gear, third gear. First gear will be nothing but smaller engaged to bigger. Second, more or less same. Third, same. Fourth one, okay, larger gear attached to a smaller gear, where you can give the entire power for converting into speed, because torque has been pulled, inertia has been overcome. So what should be the number of teeth in the pinion gear, driver gear? Minimum number of teeth to avoid interference. This is the formula. ZP. What is Z? Gear ratio, phi pressure angle. AW is the ratio of addendum and module of gear. AW is nothing but fraction into module. Always for finding out the addendum, how much I should keep for gear teeth, what I will do, take module, multiply by a factor or multiply by a percentage, 20%, 35%, like that. Right. So these are all the values for G is equal to 1. Similarly, for rack and pinion, rack means flat gear with infinite center of radius of curvature. Infinite radius of curvature. Okay, no problem. Go on. With infinite radius of curvature. So there also we calculate for Z for pinion only. So ZP is equal to 2 by sin square phi. So it will be 14 number of teeth, phi 20 degrees. Note this down. Any doubt, please ask. How much conceptualization you have for the fundamentals, that will be your grade score. How much understanding you have the concept of a equation, that much will be your gate score. So without any conceptualization or understanding, it's very difficult to get gate score. Yeah, so no, full, what is the depth of the full teeth? We say that it is 2.25 times the module. See, if you do this, there is a possibility of interference. What will happen is pinion teeth will get cut off by the driver or the wheel. Hmm? To avoid, what we do, we take this value itself and reduce it to certain extent. Say some 1/5 of this value, 1/4 of the value. That if you use as the height of the teeth will be enough to avoid interference. Don't use as a whole 2.25 mm. Using stub teeth of which height is less than that of the full depth. Yeah, reducing the height. So have anybody appeared for gate, have a gate score and trying to improve? Anybody's having gate score here, appearing for second time, third time, like that? Yeah. How much you have gate score? Around 360. Oh, okay. Where you got? Oh, you're not applied. Okay, okay. Right, right. Okay. So this is design of gears. See, we have got gear trains also. Then we have got concepts like arc of contact, path of contact. All those are not appearing here. So this book is mainly based on what type of questions are getting repeated for the past 20 years, past 10 years, 15 years, like that. So you can learn like this also. So design of gears based on the load transmitted. Okay. While the transmitted load is concerned, we consider only FT. Normal part neglected. It is the tangential loads which is going to create a failure at the tip, not at the tip, at the root. Okay, right. So F F small t is nothing but design power divided by pitch circle velocity. What is meant by CS? Service factor and velocity factor. CS is nothing but design torque by rated torque. What is the maximum bending stress that appears on the tooth? So take up this FT load, okay, divided by area. So when this load is going to act like this, your area of concern will be like this. Hmm? One will be H. This will be, yeah, this is the area of cross section, H into T. See, bending moment will be nothing but Ft into H. Okay, this T by 2 is nothing but sigma B by Y. Y I am taking to the right hand side, that will be nothing but T by 2. Because when the teeth bends like this, it will be tensile stress here, and this will be compressive stress here, and that value will be maximum at T by 2. That's nothing but T by 2. Hmm? See, M is equal to Ft into H. Y is equal to T by 2. So sigma B by Y is equal to M by I. Got it? Right. And when you look from the top, okay, sorry, when we look from the top, your cross section will be like this. Hmm? This will be T, and this will be B. So your axis is like this. Always, when you write moment of inertia expression, you will get a doubt. BT cube or TB cube. These problems will definitely come in exam. You will tell you what should be done here. Okay. Select the dimension that is perpendicular to the axis. Which dimension? T. You cube the dimension. Take the other dimension only once. So BT cube by 12. It is here. Got it? Hmm? Dimension that is perpendicular to the axis of our consideration has to be cubed. That keep in mind. And then you write it out. These are the places where you will commit mistake in the exam. So therefore, F capital T will be equal to T will get cancelled. So what you do, you keep Ft on the right hand side and bring all these to the left hand side. So when you do so, B sigma B T square by 6H, multiply by module, divide by module, T square by 6HM, that you call it as Y. This Y is nothing but dimensionless parameter known as Lewis form factor. And Y by pi is called as form factor. Hmm? Now, how see we, this expression is simply based on bending theory. We assume it as a beam. I'll write it here. Based on bending. Assumed as beam. Assumed as beam. Hmm? Note it down. What? CV is nothing but your velocity factor. You will see at the time of problems. See, it is given as CV divided by KF. CV is nothing but velocity factor. KF nothing but stress concentration factor. And CS we have not used it very well anywhere. CS will be using at the time of design torque and rated torque. Normal part of load neglected. Got it? We consider only tangential load part, not the normal part. Gear tooth is very short, but even then you use an approximation called cantilever beam and we use the bending equation sigma by y equal to m by I equal to E by R. That we will see. What is the value of CS will at the time of problems we will see. Okay. Design torque, when you say design value divided by rated value, most probably it will be greater than 1 only. Rated value means what the maximum machine can withstand, nothing but the load that we are going to get. When you say design value means the ultimate value, yield value. So when you divide, obviously it will be greater than 1. So for SOM and engineering mechanics, how many hours was allotted? For engineering mechanics, how many hours? Like this 7 hours, 10 to 5, 10 to 5, right? Okay, then for SOM, how many? 10 to 6. Oh, only 6 hours. Oh, 6 classes like this for SOM. For engineering mechanics, how many classes were allotted like this? How many days? Do you remember? 3. Okay, we'll go to the next slide then. Right. What about in transmission of loads for design of gears? If dynamic load comes, how will you consider? Ft plus Fi. Ft is nothing but the force transmitted, and Fi is something but the incremental loads, nothing but the inertial loads. Okay, both added. Take Fd value and substitute in the previous equation. That is for dynamic loading. Right. Then check for wear and tear of the gear. This is Buckingham's equation. Okay. Zp and Zg are nothing but number of teeth in the pinion and gear wheel. Ep and Eg are nothing but Young's modulus of pinion and gear. Phi is nothing but pressure angle. dp is something but pitch circle diameter of pinion. Everything we take in terms of pinion. We design the pinion only. Right. Similarly, sigma e, yes, endurance limit for repeated loads. Okay. B is something but width, and dp is something but pitch circle diameter. So your wear load should be 1.5 that of the dynamic load for best design. Which one, pa? Sigma ES is something but the endurance limit for repetitive loading. If you are designing for pinion, sigma EP you have to put here. If you are designing for gear, sigma G square you should put. This is Buckingham's equation. Your wear load should be greater than or equal to 1.5 times the dynamic load. Right. So, rolling contact bearing. We are moving from shaft to bearing. Okay. Why we need a bearing first? Any rotating member will be always subjected to a centrifugal pull, radial outward pull from its axis for each and every rev, for each and every revolution. If suppose a shaft is rotating at 1000 rpm, there will be 1000 centrifugal pull from the axis. Okay, radially outward. I'll draw the diagram. If it is pulled outside from axis centrifugally, radially outwardly, end bearings will bring back the shaft. So if you say 1000 rpm, 1000 times it's getting pulled, 1000 times the brain is bringing and putting the shaft under normal alignment. That is why a bearing is needed. Bearing at the ends. For each, and if you say 1000 rpm for a shaft, 1000 times it will get pulled for each and every revolution. So what will the bearings do? The outwardly going shaft will be pulled and will be kept under proper alignment. The bearing is pulling and bringing it back. That is centripetal. The rotational pull outside is called centrifugal. That's the reason we are using bearing. Else the shaft will fly away. Okay. So rolling contact bearing. Static load carrying capacity. Okay. So the relationship between Z diameter, K is a constant of proportionality. Okay. This C naught is something but static load carrying capacity. Number of balls is Z, diameter is D for the balls between the rollers. Strebec's equation. So what is dynamic load carrying capacity of bearing? Radial load for which a bearing can withstand 10 power 6 revolutions is called the dynamic load carrying capacity of a bearing. I said, isn't it? Radially outward pull. So 10 power 6 times, if it can withstand, we call it as dynamic load of the bearing. What is my equivalent dynamic load? Fr is nothing but radial load, Fa is nothing but axial load. Okay, X and Y are nothing but thrust and radial factors. V is the race rotation factor. Value of X and Y depends on Fa by Fr, and Y depends on Fa by C naught, where C naught is the static load carrying capacity. So I'm taking a set of bearings. Okay, if a bearing has 90% of reliability, it means that 90 bearing of same type will fail over 100 for a given life. I'm having a set of bearings. Okay, it's in that there are 100 in number. 90 bearings will fail. Okay, that is called as 90% reliability. If I bring another set, say some totally 35 number, how many of them will fail? That is nothing but reliability R. Take one set, in that if it is 100 is a number, 90 will fail. That is nothing but reliability of 90 bearings by 100. Take another batch, which will be say 40 or 50 in number. In that, how many will fail? What is the reliability? That is nothing but L by L 90. This is 90 by 100 batch. This is the given lot. Okay. Here we are using a design for finite life. That's the reason we are using two batch size. One ideal batch. Among 100, 90 will fail. So if you take one more lot, what will be the reliability? Since we are using a finite life here. If it is infinite life, no problem at all. Give one bearing into the hands of the customer and use that way you want till it breaks. But here what you have done is that you have done a finite life calculation. So we need to have an idea. One particular bearing, this much life is coming. Why not the other? So that we can interchange. There is something called interchangeability. Okay? That is why we are taking this. So when we sell components based on this finite life, what we will do, we will take one component, we will run it in laboratory, we will switch on the motor, and finally note down how many cycles it has come. Okay. Then whatever we manufacture, we give them as a specification. 90% of life, 80% of life, 70% of life. That is why we are doing this. We need to have an idea. And moreover, while finite life is concerned, we have certain calculations like bearing load subjected to bending only, bearing load subjected to torsion only, bearing load subjected to combined torsion and bearing and bending. Okay. So when we give the bearing to the customer, we are not confident that the customer will take up only bending load, only torsional load. Any load he can take up. If suppose he is taking combination of all the three, at that time we need to give a specification like this. Do you understand? So because this fatigue life and all experimental data, based on experimental data only, we are saying that 10 power 6, 10 power 3 like that. So I need to have one standard in my hand before I give the product to the customer. And then I need to say that whatever you purchase from me, it will perform 90% of what I have as an experimental value. That's why we are putting it as L90 and L, R90 and R. Because this is finite life, okay. The person will definitely ask, how many years will it come? At the time I need to answer. To answer, I need to have one experiment done. Then only I can answer. So if experimental data is has come for 3 years, when I sell the product, I will say that in and around 3 years. That is what? L by L90, R by R90. R90, L90 is my experimental value. L and R is nothing but what I give to the customer. Because certain people ask why L90 and L should come. Simply take the bearing and give it to the hands. No, that like we cannot say like that. One person may use it for mild loads. One person may use it so heavily. Both of them, if they come at the same time, it will become a problem. Okay. Therefore, see, B is just a design factor like stress concentration factor. All these are based on the experimental values and thumb rules. No much logic in values and all. You don't need to bother about that. Okay. Okay. Load life calculation. See what you do. For n power 6 cycles, how many hours it has worked? Okay. Therefore, for 1000 cycles, how many hours will it work? Simple calculation. It's nothing but the load life calculation. L is equal to C by B power whole power n, where n is nothing but 3 for ball bearings, 10 by 3 for roller bearings. C is nothing but the dynamic load carrying capacity. P is nothing but equivalent dynamic load. This L is equal to 60 n LH by 10 power 6 is nothing but life for 10 power 6. Therefore, life for how many hours? 10 power 6 is the standard value, design value. And n is nothing but what we are going to operate. How many hours will it come? So for 10 power 6 cycles, what is the life? Therefore, for n revolutions, for n cycles, what is the life? LH. Like that we are calculating. Always dynamic, fatigue components. Components are subject to fatigue loads. You need to have one experimental value, then only you can sell the component. Design value should be always present very strongly in our hands. Then only we can speak to the customer. Simply if it is infinite life, no problem at all. No one want any experimental value. If you hang a fan like this, after 10 years also it will be like this only. Simply we can give it to the hands. And we can say that it is infinite. But finite means you have to come out in the value. 2 years, 3 years, 7 months, 6 months, all these you need to say. That is why we are calculating all these values. Okay. Sliding contact bearing. There are certain concepts in this. Thick film lubrication. See, this is the bearing. This is the journal of the shaft. You will be filled up with oil here. Okay. So as the centrifugal force of rotation speed increases, this journal will be lifted upwards since oil is going to fill up inside. This is called thick film lubrication. a layer of oil will come between journal and the bearing. So it will lift the journal, rotating journal. If there is no lubrication effect like this, for creating pressure, if we use one external pump, it is called hydrostatic lubrication bearing. It is called as externally pressurized. Okay, and what is the advantage? Since we are using a pump, high load can be carried, and no starting friction, no rubbing action, because the moment we switch on the pump, since it's being operated by a motor, pressure rise will be so high, all of a sudden the journal will lift up. So no friction, no rubbing action. Whereas this hydrodynamic is concerned, first this journal will be in contact with the bearing. As soon as it starts rotating, rubbing action, friction, everything will be present. As you slowly push the oil in between the journal and the bearing, slowly it will get lifted up. So starting torque is very high for this hydrodynamic lubrication. It is less for this hydrostatic because it's externally pressurized. What do you mean by thin film lubrication? See, this contact space between journal and bearing is there, right? If it is thick, means thick film lubrication. If it is so small, it is called as thin film. There will be a relative velocity between the two, rubbing against each other. Partial metal to metal contact, right? There are certain clearances. Okay, diametral clearance means CD is nothing but capital D minus small d. D is the diameter of the journal, D is the diameter of the bearing. And this CD, if you divide by 2, it is radial clearance. What is meant by eccentricity ratio? E means the distance between center of the journal shaft and center of the bearing. This is nothing but E. There are two centers you have to remember. So epsilon is equal to E by the CR, means eccentricity ratio. There are two types of thickness. One, minimum film thickness. Other one, film thickness at any angle of rotation. When you say minimum film thickness, okay, it will be C by 2 minus H naught. Okay, this is the H naught, this value. CD by 2 minus H naught. CD is nothing but what? Capital D minus small d. So capital D minus small d, you will get a distance like this here. From here to here, you will get minimum film thickness. Then film thickness at any angle phi, you can this formula. I'll expand this, okay? CD by 2 plus epsilon means E divided by CD by 2 into CD by 2 cos phi. Eraser. This is at any angle. Okay. Same formula, this is CD. Same formula, use it here, plus this E, you resolve it along the axial direction. E cos phi. So at an angle phi, this distance plus this distance is nothing but your clearance. Okay, so how will you do so? CD by 2 means what? Capital D minus small d. Okay, right? You will get this distance plus this smaller distance. The smaller distance is nothing but E cos phi. This E, you resolve it here along this axis, you will get this distance. Then the remaining portion above and below will be capital D minus small d. Right. So there are two types of thickness. One minimum fill thickness measured in this direction. Other one at any angle phi in the vertical direction. Yeah. See, angle is defined between this vertical axis and this eccentricity distance. This point and this point, if you join, you will get small e. So this angle is nothing but phi. So one you can measure here vertically. Other one you will make it here radially. When you use radially, you will have a minimum thickness, right? That is nothing but the minimum fill thickness. That how will you do is nothing but capital D minus small d. Okay, you will be left out of the distance. In that you remove off this h naught here. When you say in the vertical direction, you need to add this one. So plus E resolved along this one, E cos phi. Okay, CD by 2, CD by 2 constant for both minimum film thickness and any angle phi constant. In one you should add cos phi, E cos phi. In one you should remove off this h naught. Okay. Okay. See, radial load. Okay, this is the radial load. So now this journal is in contact here, I'll assume. I'm looking from here. Okay, so it will look like this. Now what I'm doing is I'm visualizing the area of failure, cross section area for failure. Right. So one is nothing but the length along the board. This is nothing but the L. Then the thickness, nothing but the diameter. So force divided by area, nothing but L into W. You should discuss like this. Then only you can understand. Simply learning will not help you. You will not understand the meaning. So two cylinders, concentric cylinders. Okay. One big cylinder. I'm inside there. I'm inserting a small cylinder. A patchy area will come of contact. I'm looking it radially outside. So this is how it will look like. You have to imagine, conceptualize. So when I look like this, from this point to this point is D. And what is be the length to be perpendicular to this board? That will be L. Like this you have to learn. Phi, what? See, phi, what is that? One line passing through the center of the bearing, this point, right? Another point, horizontal axis passing through the center of the journal. So join these two. So it will be like this. Sorry. Eraser. This will be phi. and this distance will be E. This is for journal or shaft. This is for bearing. Vertical axis, horizontal axis, join radially. Then the angle made with the vertical. That is nothing but your phi. Hmm. Right. Do you understand? Okay. See, when you operate, you need to have an idea at which speed to operate. Okay. So you're taking a plot between uh, coefficient of viscosity with a dimensionless number Zn by P. Okay. This Zn by P is called as bearing characteristics number. So what will happen is that coefficient of friction between journal and the bearing becomes minimum at a particular point. Right? Minimum at optimum speed. Then it increases further. P is nothing but pressure, N is nothing but speed. Okay. Z is nothing but the viscosity, where mu is nothing but coefficient of friction. Coef of friction, hmm, viscosity, N speed, pressure. Okay. Right. So Sommerfeld gave an expression called Sommerfeld number is equal to Zn dash by P into R by C, the whole square. R is the radius of the journal, C is the radial clearance. And to find out mu, coefficient of friction, Petrov gave one equation. Mu is equal to 2 pi square Zn by P, D by CD, where D is the diameter of journal, CD is nothing but the diametral clearance. Okay, note it down. So this is for thick film lubrication. It will reduce down at an optimal speed, then it will start increasing. So the lubrication changes from thin film to thick film. How to save this? Hmm. Important formulas. You see this right from the beginning. Rankin theory, Tresca's theory, Saint Venant's, Higgs theory. Okay, I missed one more. This Coulomb's More theory. See, this Coulomb's More theory, when do we follow? Both tensile and compressive load is acting on a brittle material, we'll assume. Okay, at that time, what will be the load, stress induced? So UT is coming, UC is coming. And what will be the factor of safety? Hmm? So whenever you start learning this subject, go to this formula page, write all the formula once, then take a 20 years question paper, solve all problems, repeat this 2 to 3 times, and discuss with each other conceptually. You should imagine and then be clear. Fundamentals should be very thorough. Then only you can calculate. Fundamentally, you're lagging behind something, or you're not confident, then you will get jammed. So problems, solutions, all these will take care. Note it down. Any doubts anywhere, please do ask. Don't keep silence. If they give us a further session for machine design, they said that I have to take it for 7 hours. Accordingly, I'm planned. Okay. If they give us further sessions, what I will do, I'll take 20 years question papers. I will put it in the slide and then I'll bring it here so that we can solve one by one. The same solving we'll do it now also, the afternoon session. So what I have done for each and every topic, say rivet one problem, weld one problem, gears one problem, bearing one problem, shaft one problem, like that I have taken. If they give us more hours, Right away we will start from 2004 up to we will go to 2024. Where pa? Yeah, sigma T by sigma UT.
What is sigma C?
Sigma C is the compressive stress in terms of reversing or alternating applied stress. Sigma UC is nothing but the ultimate strength in compressing load. Compressing load. Yeah. Because for a material, sigma UT and sigma UC will always be not be equal. This is called, we call it as a Boschinger effect. They have asked in many interviews also, why for a material sigma YT is not equal to sigma YC. Why is it so? That is said beginning itself. Tensile load means pulling away. Atoms move away from each other. Lesser yielding. When you compress, they'll come nearer, nearer, nearer. At one stage, one will glide over the other. Pinning, slip, dislocation, etc., etc. All yielding mechanisms will happen. So, material in compression will fail more miserably and badly than in tension, called Boschinger effect. There is some hysteresis in the material. Whenever you load, some permanent change is happening. That we call it as hysteresis.
Then why does cast iron have a higher compressive?
Where? Which one?
Cast iron. Why does it have a higher compressive?
Yes. See, steel material, the more and more you pull, atom will move away from each other. So it's more ductile in nature. But cast iron is not so. You cannot easily pull that one. It's something like glass, you assume. So if you drop cast iron, it will get shattered into pieces. That is the failure mechanism. So it will take only compressive loads. It will not allow ductile loads. So everybody of you are put up as scholars in engineering college or working somewhere. ಎಲ್ಲರೂ scholars are? You are working? Where you are working? Okay. So these are collective formulas.
What does sigma V in general have?
Sigma V is nothing but amplitude part. Usually you might have seen in book as sigma A, right? But this author is using sigma V as sigma A.
But then there is another.
Yeah, yeah, I'll tell you. Which one you're asking? Here. Yeah. Sigma means the amplitude of the varying stress, whereas sigma A means the mean part, average. So you can say that sigma A is equal to sigma max plus sigma min by 2. Sigma V means sigma max minus sigma min by 2. Yeah, you can take one. No problem. I'll also give you ebook. It's available. We'll ask the your yeah, it's there. I've given it to the group. They'll post it in your by today itself. So go for lunch by 1, turn back by 2. Then we'll start moving with the problems.